Hi dear students, welcome to today's online class. Today we discuss the remaining three mechanisms of aromatic electrophilic substitution reactions. In the previous class we discussed mechanism of halogenation as well as nitration. Today we have mechanism of sulphonation, FriedelCraft alkylation as well as FriedelCraft acylation. I think the third one is not alkylation, it is acylation. Okay. If we have gone thoroughly through the previous two mechanisms and the general mechanisms, it will be very easy to follow these three mechanisms. Let us start with mechanism of sulphonation. Okay, what is sulphonation reaction? Benzene, when treated with fuming sulfuric acid or concentrated sulfuric acid, gives benzene sulfonic acid, and water is a byproduct. The reaction can be viewed as one hydrogen on benzene ring is substituted by SO3H group. So we can write sulfuric acid as conveniently as SO3HOH, right? So what happens? H2O is removed, SO3H attached to the ring, it becomes benzene sulfonic acid and H2O is byproduct. Actually, in this reaction, if we go into the mechanism, we can see that the electrophile, the attacking reagent is SO3. It is important to note the electrophile of each reaction. In halogenation, it is halonium ion. In nitration, it is nitronium ion NO2+. Here it is SO3, sulfur trioxide. Now let us see the mechanism. Fuming sulfuric acid is sulfuric acid containing excess of SO3 dissolved in it, which is essentially found during the manufacture of sulfuric acid by contact process. If the reagent is fuming sulfuric acid, SO3, the electrophile is present there itself. If not, if we are using concentrated sulfuric acid, it produces in situ SO3 by this reaction. So generation of electrophile, which is represented before we explain the mechanism. What happens here? Two molecules of H2SO4 is undergoing autoionization, producing first H3SO4 plus and HSO4 minus. How? One molecule of H2SO4 is donating H plus to the other molecule, so that one become H3SO4 plus, and HSO4 minus, we know it will act as the Lewis base in the second step of the mechanism. Now H3SO4 plus undergo cleavage, heterolysis, producing H3O plus and SO3. So here SO3, this is the electrophile during sulfonation reaction. How SO3 become electrophile? If we look into the electronic structure of SO3, we can easily understand SO3 is having 3 double bonds with oxygen, and we know oxygen is more electronegative, so that the pi electrons due to resonance get delocalized onto oxygen. Oxygen get a delta negative minus charge, and sulfur consequently get positive charge. This happens in all these pi bonds. So due to this, sulfur become highly positive, electron deficient. So that is how SO3 act as electrophile. Now coming to the mechanism, the first step is attack by the electrophile forming sigma complex. You can easily see it here. Benzene ring is there, SO3 is there, and one pi bond from the ring is used to form bond with sulfur. So it takes place like this. We can easily understand how the bonds are formed. We show one H separately, which is going to be substituted. So it is like this. I am showing one oxygen separately and the remaining two oxygen like this. So we know sulfur is positive, so this pi electron from benzene used to form bond with sulfur, attack on sulfur. So this pi bond will shift to oxygen. Okay. So what happens? It forms the bonds. It will become the intermediate rhenium ion like this. What you get is this. There will be H here and SO3 will become now, there will be one negative charge on oxygen, so we write SO3 minus, and these two bonds are intact. This is called sigma complex or rhenium ion, which is resonance stabilized. The next two structures are the resonance structures for this intermediate. It is obtained by shifting the pi bond inside the ring like this, you know. First, okay, of course, there is a positive charge over here. There is a rhenium ion and there is a negative charge on oxygen outside also. So first this pi bond will move to this place and then this will move to this place and you get three structures, and the resonance hybrid is also shown. Okay. Now the second step is loss of proton. So electrophile has come in, now H plus has to go, for which HSO4 minus, which is produced during generation of electrophile, which act as the Lewis base. This HSO4 minus is the Lewis base, which will abstract the proton, forming benzene sulfonate ion. That is not the product. SO3 minus is formed, C6H5 SO3 minus is formed, plus H2SO4. This H2SO4 is the catalyst actually in the reaction. At the same time, it is a dehydrating agent also, shifting the equilibrium to the right. It is regenerated in this step, consumed in the first step, and finally there is one more equation, that is SO3 minus has to become SO3H, that is by interacting with H3O plus, which is formed in this step. You can see there is H3O plus here. You can see that here. This H3O plus is shown in the last step. Okay. So it becomes HSSO3H, the product benzene sulfonic acid plus H2O, that is a byproduct. This is mechanism of sulfonation. Okay. Now the next one, FriedelCraft reactions, which consists of two reactions, FriedelCraft alkylation as well as acylation. What is alkylation reaction? On benzene ring we introduce alkyl groups, generally writing RX, and we know for FriedelCraft reactions we need a catalyst, that is FriedelCraft catalyst, which is generally anhydrous aluminum chloride used, which is a Lewis acid, which can accept electron and act as a catalyst here. You can as well use BF3, anhydrous zinc chloride, FeCl3, etc., which are also used as FriedelCraft catalyst, but most common is anhydrous aluminum chloride. So if RX is used, it forms alkyl benzene, right? Alkyl benzene is formed. Taking specific example, if we take methyl chloride or chloromethane and AlCl3, you get methyl group here substituted, then we call that is toluene. If we take ethyl chloride, then the alkyl group substituted is ethyl group, so that is ethyl benzene. Like that, we can prepare any alkylated benzene compounds. A limitation for alkylation is that if we are using long chain alkyl groups, then you may get rearranged products, which you will understand from the mechanism. Let's go to mechanism now. As usual, initially it is generation of electrophile. RCl or alkyl halide interacting with the catalyst, that is AlCl3. We know that AlCl3 is an Lewis acid which can accept electron. So what happens? RCl or Rx, when it interact with AlCl3, what happens is that there is lone pair on chlorine which will be used to form a bond between chlorine and Al. A bond is partially formed between aluminum and chlorine. That will weaken this bond. This RCl bond become weak. When one bond is formed here, it is at the cost of the other bond. The neighboring bond become weak. That's quite natural. Eventually, it breaks as R+. So R+ is the electrophile. Alkyl cation, which is a carbocation, is the electrophile during FriedelCraft alkylation reaction. Plus AlCl4 minus, that is now a Lewis base which will act in the second step of the mechanism. Coming to the two steps in mechanism, once the electrophile is generated, it will attack benzene ring, forming the sigma complex as usual. It's now very clear to you. It's analogous. So sigma complex is formed, adenine ion is formed, which is resonance stabilized. We shift the pi bonds towards the electron deficient carbon, forming the next two structures. There are three structures here, very important. Three resonance structures here. Three structures here. And we represent the resonance hybrid here. In the second step, H is removed as H plus using the Lewis base, that is AlCl4 minus. It will take away H plus, so that sigma bond get back to the ring and ring recover its complete aromaticity. So you get the alkyl benzene as a product. This H plus will combine with the Cl minus in AlCl4 minus, forming HCl, and AlCl3, that is a catalyst, is regenerated. Okay. Now a limitation of this reaction is that a limitation of FriedelCraft alkylation is that it will lead to rearranged product. That means, suppose you are using your taking 1-chloropropane or normal propyl chloride as the alkyl group. See this one, chloropropane, 1-chloropropane. We are taking this as the reagent in presence of AlCl3. Treating with benzene, we expect what? We expect this propyl group or normal propyl group to attach to benzene. That means we expect normal propyl benzene as a product. But it is found that the major product is found to be isopropyl benzene. How it happens? In the mechanism, we know first of all the carbocation is formed. This is a primary carbocation, right? It will rearrange to more stable secondary carbocation by shifting of one hydrogen from this carbon to this one, so that the carbocation charge comes here. It becomes a secondary carbocation or isopropyl carbocation, which attack benzene ring, forming isopropyl benzene instead of normal propyl benzene. You get actually both product. Major product will be isopropyl benzene. So this rearranged product is possible during FriedelCraft alkylation. That is one limitation of FriedelCraft alkylation. Okay. Now finally we have FriedelCraft acylation. What is acyl group? Acyl group is generally represented RCO. This is acyl, which is part of carboxylic acid, RCOOH. RCO is called acyl group. If R is CH3, that means CH3CO is called acetyl, specific name, which is part of acetic acid. So this is acetyl, RCO is acyl. Okay, let us see the reactions here. Benzene when treated with acyl halide and AlCl3, you get acyl benzene. RCO group is substituted on the ring. Here a very important point is that when you write the structure of the product, you may wrongly write like this. This is absolutely wrong. You should write C is to be bonded. You can see it here. It is COR. It's to be written like this. Attachment is to carbon, not to R. R cannot come in between, right? You know that. So that is an important point when writing the structure. Okay. Now, this is a general example. Specific example we can see down. If you take benzene is treated with acetyl chloride, CH3COCl, right, or ethanoyl chloride, that is IUP's name, in presence of AlCl3 at a little high temperature, you get acetophenone, that is a product. This is acetophenone. IUP is the accepted name, or it is acetyl benzene. Now see that for acylation, to introduce acyl group, the best reagent is acid halide, like this, acetyl chloride you can take. Instead, you can also take acetic anhydride, which also contain acetyl group. So acid anhydride can also be used for FriedelCraft acylation. So you have two options for the reagent: acyl halide or acid anhydride. The difference is that the byproduct will be different. If you're taking acetyl chloride, the byproduct is HCl. If you're using acetic anhydride, the byproduct is acetic acid, or in general carboxylic acid. Coming to mechanism. As usual, the first step is generation of electrophile. RCOCl interact with AlCl3. Being Lewis acid, it form a partial bond with chlorine. Aluminum and chlorine get bonded here, and the bond between CO and Cl weakens and it breaks, forming this RCO. Sorry, this is single bond. RCO plus, that is called acyl carbocation or acylium ion. We can simply call it acylium ion. The advantage of this acylium ion is that it is resonance stabilized, because the lone pair on oxygen can shift here and become a triple bond and positive charge appear on oxygen. So due to this resonance stabilization, acylium ion is quite stable. Okay, so it will not undergo any rearrangement, unlike in the case of FriedelCraft alkylation, where the alkyl cation or carbocation may undergo rearrangement, forming more stable carbocation. That doesn't happen here. So this is the advantage of FriedelCraft acylation. You get intended product, no rearranged product. Okay, let's go to the mechanism. Step 1, as usual, attack of the electrophile. What is electrophile here? Acylium ion that attack the ring, forming the sigma complex or rhenium ion. As usual, it is resonance stabilized. And the second step, AlCl4 minus, that is the Lewis base, abstract hydrogen as H plus, forming the product, that is acyl benzene, and the byproducts are HCl and AlCl3. Okay, so that's all the mechanism of various aromatic electrophilic substitution reactions, or what we call the famous 5: halogenation, nitration, sulphonation, FriedelCraft alkylation, as well as FriedelCraft acylation. You should practice writing all these mechanisms so that you become thorough with it. You can propose mechanism for any of the reactions if it is asked. Thank you.